But I'll just introduce another problem, which is a classic dynamic programming problem. And this is, it's called Longest Common Subsequence. So, those of you are you familiar with this Linux utility diff? Right? So what does diff do? Yeah?
Finds the differences between like two files.
Right. And basically it's like two strings, right? You give it two strings and it tells you what the differences are. And so how does diff actually solve that? It's also, if you think about it, it's like a discrete optimization problem. So I give you one string, I have to remove and change a bunch of things and get to another string. And it's kind of saying, what is the best way of doing that? So let me sort of state this problem explicitly. So I'll say a subsequence not substring. A subsequence of a string is formed by taking a subset of the characters in the same order. So, for example, let me look at the string. Right? So let me look at the string. So a possible subsequence I can get is sing. I can get tin. I can get sting. I can get sin. So on and so forth. So I don't have to take them to be contiguous. They don't have to be near each other. If it's contiguous, it's called a substring. Right? So ring is a substring, but sing is a subsequence, not a substring.
But a substring is also a subsequence.
Yes. A substring is also a subsequence. Right? So one way in which I can represent this is, again, just like, do I pick this or not? Right? So if I wanted to get sing, I would say pick, don't pick, don't pick, 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 pick. So for an n character string, how many subsequences? Is it n choose 2? Is it 2 to the n? Or is it n factorial? Yeah? Yes? Ring is a subsequence. It is also a substring. Yeah. And just I'll repeat that. A substring is also a subsequence, but a subsequence may not be a substring. Right? Because I just form a subset of the characters, not an interval of characters. Yeah. Okay, so what is the answer? Okay, so by now we've seen enough of these discrete math examples. We know it's 2 to the n, and it's 2 to the n exactly because for each, I can either choose to keep it or not. So there are two options for each, and you get 2 to the n. Right? And so, get my notes out of the way. Next is 53. And so this is called the LCS, the longest common subsequence problem. Given two strings, find the length of the longest common subsequence. So what does that mean? So suppose I take string, okay, and I take, this wasn't the best example. Let me think of another one. And I take spin. I take these two. So what is the longest possible subsequence? Sin, right? But Sn is also a valid one, so is In, right? But in this case, sin works because I could take these three that way, or I could take it from, right? And so the LCS length is equal to 3. And so the question is, can we get a polynomial time algorithm to compute LCS? And the way I'll think about it is I have two strings whose length is m and n. Okay. So I gave you an example of one place where they actually compute LCS, diff. If you run diff on two files, it's basically computing an LCS. Does anyone know of another very important example where people actually compute LCSs of strings? Yeah? DNA sequencing, exactly. So if you take a DNA sequence, it's a string. It's A, T, G, C. It's a long string of 4 characters, right? And so when the pandemic hit and they were doing all these things like, oh, now there's a new alpha and then there's a delta, and this is just a variation of delta. How do they figure that out? They were sequencing the DNA, computing LCS, and looking at the differences. And they'll say, oh, this is actually pretty close to that, so on and so forth. So a lot of sequencing of the human genome or any kind of genome there's a lot of string algorithms. And LCS is like one of the most fundamental string algorithms used for that. And this is also so what I'll do is, I know it's just a few minutes left. I'll just write down a few things. We'll do it again in the next lecture. But if you set this up as a recursive procedure, you'll see the same features. There's a recursive algorithm. From that, you can look at the overlapping subproblems, and then from there you can build a table. So how does the recursion work? So I'm just going to call my two strings A, which has length m, and B, which has length n. So what are the sort of options? I can look at the last character of those. If they match up, then I get a recursive problem. Right? And if they don't match up, then I have to give up on one of them in the common subsequence. So I can give up on the first one, or I can give up on the second one, and then again I have a recursive problem. So basically we end up with 3 choices. Each of those you can write down as a recursive subproblem, and then you just maximize on those. And that gives you a pretty straightforward algorithm for LCS, which is actually the best, up to some few changes, is like the best algorithm that we know. Yeah?
Can't you also take neither?
You could drop both, but that case is actually subsumed in just dropping one of them. If you drop one of them, eventually the other one will get dropped. Yeah. Okay, so I'll just write down these 3 cases. So I'll say if A of m minus 1 is equal to B of n minus 1, so these characters are the same, then you can just do LCS of A. Maybe I'll write this as 0 going to m minus 1, B 0 going to m minus 2. Yeah, my indexing is wrong. Yeah. Then I get this. I could drop a m minus 1, in which case I'll just get the LCS value of a 0 going to m minus 2, but b still going all the way to the end. Or I could drop b of n minus 1, and then I keep a, but then I remove one character in b. Right? So this is saying that either I match these, or I drop one character, I drop this, I just look at the LCS of what's left, or I drop this and look at the LCS of what's left. And again, I could then just take the maximum of these three cases. I just take the maximum of these three cases. So this gives me a recursive algorithm, which again, if I were to run sort of naively, I might think like I have like multiple options, so I'm getting lots of recursive calls. But you see the arguments are actually pretty simple. The arguments are always prefixes of A or B. It's like the first so many characters. So actually the total number of choices for the first argument is m, the total number of choices for the second one is n, and it's mn. And so you get an mn time algorithm to do this. Okay? So next lecture we'll go over this example again, and I will try to post out like a small dynamic programming homework to do. Okay? All right.